Okay, I guess it's exactly time to start. Welcome everybody to our weekly series of seminars. Today we're very happy to have Mukhametzhanov from the IS. He'll tell us about Beurling, I'm not sure I'm pronouncing it correctly, Selberg extremization and modular bootstrap at high energies.
Yeah, all right. Thank you for the invitation to speak. So my talk based on these papers I've written with Sasha Bayedov and 3D Pal. And some of you may have already heard me maybe speaking about this first paper, so I apologize for that. But the second part will hopefully can still learn something new. All right, so let's see. So let's consider just some crossing equation. Let's say, well, I will consider partition function and modular bootstrap, or it can be a 4-point function in any number of dimensions or something like that. And let's take just the most standard, simplest Euclidean OP limit. And then in one channel, so you have this vacuum contribution. You can see my pointer, right?
Yes.
Okay, yeah, that's good. So in one channel, we have, let's say, vacuum contribution. And in the dual channel, this is supposed to describe some some properties of the details of the high energy states. And there's been, of course, worked out many examples of this type, and sometimes these are called crossing kernels, that you take, let's say, the vacuum and you expand it in the conformal blocks in the dual channel and rid of the spectrum. And so this is, I think, can be naturally called a coarse-grained approximation, because the information that you typically get in this way is in some sense coarse, that it has to be averaged over a certain range of energies, and that's what usually you get in this approximation. And this approximation is very useful for some things. For example, it captures thermodynamics of high energy states very well. And so a famous example is this 2D modular invariance of the partition function, that you have a partition function which is approximated at high temperatures by the vacuum, and then it describes some thermodynamics of high energy states in this dual channel. Famously derived by Cardy, and then also related to the black hole entropy by Strominger. So while this approximation is extremely useful for some things, still it doesn't know everything about high energy states, and there are some features which can be naturally called fine-grained features of high energy states, which are not described in this simple approximation. And so some basic example of that is just the discreteness of high energy states. So often in this approximation, you naively get the continuous spectrum of high energy states. And this is kind of reminiscent of this version of information paradox in ADS. Another important example is that in many theories, in many chaotic theories, we actually expect the high energy states to obey random matrix statistics, and this is certainly not captured in the coarse-grained approximation. And so ideally, one would like to understand this kind of more fine-grained features, but generally, this is a hard question, and so perhaps it's natural then to, before going into these finer details, to better understand this coarse approximation. And so what are the limitations of this coarse approximation better? And so this is the goal of this work, sort of, so to put this approximation on firmer ground and this, of course, entails simply treating these tails more carefully, because this is kind of just the source of all the puzzles and paradoxes. And along the way, we will get some new interesting quantitative results about hierarchy states, and in particular, quantify what we mean by coarseness, what kind of averaging we have to do, and so on. And so this is, so this is the motivation. And now let me, unless there are any questions, I will move on to my main example. Okay, so my main example for today will be just the simplest thing possible. I'll just consider the partition function on a two-dimensional torus, which is at high temperatures approximated by the vacuum, and we have some discrete spectrum, let's say. And then we would like to derive Cardy formula from this somehow. For hierarchy states. Fun fact is that if you actually look at the paper by Cardy, which everybody cites when people write down this formula, you will not find this formula in there, and you will find this formula there, but not this one. And this I suspect for a good reason, because this formula is somewhat imprecise. And so let me explain that. And so naively, you would like to just take the partition function and take the inverse Laplace transform. So we integrate our imaginary betas and we expand in the dual channel. And so for sufficiently small betas, indeed, this is dominated by this vacuum contribution. And if you integrate it, you would get Cardy growth, Cardy behavior. But then for larger betas, all the other terms actually become relevant, and they become of the same order as the first term. And so the approximation by just the vacuum is not valid. But then you would like to say that perhaps, well, for large delta, this is an oscillating phase. So perhaps only small beta matter in this formula. But well, as far as I'm concerned, so this kind of intuition is usually based on Riemann-Lebesgue lemma. And here it is not applicable because this function which we're integrating is not integrable. So that's what you need for Riemann-Lebesgue lemma. And this is essentially because of Poincare recurrences. That's so this z, it's as a function of t, it's a sum of oscillating phases. And so once in a while, the phases come back into sync, and it takes the value close to the value at t equals 0 infinitely many times. And so this function is not integral, and you cannot apply this lemma. And this is, of course, not, well, this may be not too surprising, because really this formula is computing what you might call a fine-grained density, so that it's an exact density which is very sensitive to the precise value of delta, especially if, well, if rho is the sum of delta functions, then it's either 0 or infinite. And we actually don't expect to compute this formula instead we expect to compute, of course, this coarse-grained version, which is a microcanonical density of states. But then the question remains, so how do you derive this formula? And that's what I'm gonna explain next. But this is a good time for questions, if there's any.
Hey, Bar, could you say more what this integrability was of z? I didn't fully understand. What is the statement? What are you integrating t in the first formula?
So here you mean what's this integrability of z constraint?
What are you integrating? The t?
So I'm integrating, I'm considering this integral of partition function at complex values of.
So you mean this first integral is not well defined?
I'm saying that, so what I was trying to say is that, so this approximation by the vacuum is good only for small beta, right? But in the integral, we take delta to be large, right? Then you might want to argue that beta, only small beta contribute here, and for such
I meant
beta,
for
you
the
can
first integral over t, right? In the second equation, there is no z, so
no,
you're
sorry,
not
that's the first, that's the same equation. The z is expanded here in the dual channel like that. This z is just this thing, this sum in the brackets in the dual channel. So this beta here is epsilon plus it. I just changed variables.
Okay, thanks.
I hope that answers the question. Okay. All right, so let me explain now this how you derive this formula. And so the idea is the following. So what we would like to count the number of states in this window from centered at large delta and of size 2 times small delta. And so now let's imagine we find these functions phi plus and phi minus, which approximate it from above and approximate this characteristic function from above and below, like this. And then also it will be convenient, you'll see why momentarily, to multiply this left and right side by these exponential prefactors. So you can do that because, for example, this exponent, it's larger than 1 inside of this interval, and it's positive everywhere outside. So you can just multiply it without changing the inequality. And similarly, this exponent is smaller than 1 inside, and it's positive everywhere outside. Then we multiply this inequality by the density of states, and we integrate over delta prime. And so this density of states multiplied by this exponent is almost the partition function, except for these phi's. But so we can just take the Fourier transform of these phi's, and eventually you get this formula that instead you integrate the Fourier transform, these phi hats. You integrate them with the partition function. So this beta comes from these prefactors. So far this beta is an arbitrary parameter, and this t comes from the Fourier transform. And in the middle we get precisely this thing that we wanted to bound. And so you get this inequality. So let's look at it a little more closely. So these integrals that appear here, they are reminiscent of inverse Laplace transform that we considered before. That's in the sense that we take the partition function and we integrate it over imaginary inverse temperatures. But now we have actually more control because we have these kernels inside, which are totally up to us, right? So in particular, we saw before that there was a troubling region of when t is sufficiently large, the approximation by the vacuum is not valid and we lose control. And so in particular, because of that, we can just choose these phi hats to have finite supports. Supports of t smaller than some parameter, which I will call lambda. Okay, and so this will cut off the region where we do not know what's happening. And so the functions phi, whose Fourier has finite support, are band-limited functions. So band-limited. So this is not necessary to consider other functions as long as you may know some more about this z. But for us, for now, we'll just see what we can get from this. And the rest will be discussing properties and inequalities and how to compute them and so on. Those similar ideas appear before in the works of Shiao and Rychkov, and also in more classic works by Karamata in the context of Tauberian theorems. Okay, so now let's discuss in more details how you compute these things. Before, I guess, we actually compute it, let me also say a few heuristic comments about this z as a function of t. So the z is often called, well, its absolute value is often called the spectral form factor. And so let me make a few heuristic comments, which hopefully will give some intuition of what is this function. So this function typically has the following behavior. That's if you take beta small and then consider it as a function of t, then at small times, this function is large. You just have a sum of positive exponents. And then as time goes, you have some initial decay because of dephasing. Usually it's exponential decay. And then it sets off to some small value. And then after some time, the phases can come back into sync, and there's some recurrence happens, usually only partial. And then it goes on and does similar things. Now, in the context of 2D CFTs, this region of small t, when beta is also small, is controlled by the dual vacuum, as we discussed. And so we know what's happening in this region, and that's why we constrain the integral to this region. But we don't really know what's happening in these other regions, and here it's not completely universal, so we don't know what's happening there. And there's a recurrence time. And in fact, this kind of picture suggests that we should cut off the integral at the value which is bounded by this recurrence time heuristically, but we'll make it we'll make this more precise. Okay, so this is some intuition, but now let's actually take these inequalities and see what we can get. So now we bound, we take the function phi hat to be a finite support. And now we also take delta to be large, and we also take this parameter beta to be small. Later we will relate them. But for now it's an arbitrary parameter. So now we would like to compute this integral. So to compute this integral, it is convenient to, well, first of all, we would like to take the dual of the partition function, right? Because we expect the universality to come from the dual vacuum contribution. And then we will split this partition function into light operators, which have contributions only from operators below C over 12, and into heavy operators for operators above C over 12. The point of this splitting is that we will show now that for these light operators, this integral is dominated by small t near 0. And for heavy operators, the integral will be dominated by t close to the edges, close to lambda. So that's what we would like to show. So now let's discuss the light operators. So light operators, you just compute this integral. You just have finite number of light operators here, and so vacuum dominates. Well, you have this exponential factor from the vacuum, and clearly it's very large at t equals 0. So you just compute it by the saddle approximation. So it's the value on the saddle, fluctuations, and also the value of the saddle. And there's a finite number of light operators which give subleading contribution. And this will lead later to Cardi behavior. Now, the heavy operators are the ones which are above C/12. And we would like to estimate this partition function for the heavy operators. So the thing that we can do is drop the phases. So it will be a sum of these exponents, but where I take only the real part of the effective temperature. And now we would like to compute this integral. And in this integral, each of these contributions, each of these exponents, just because this factor delta prime minus C/12 is positive for heavy operators, it's easy to see that this exponent is the largest when t is the largest. So, and because of that, we can just substitute t by lambda by the largest t that we have in the integral, and estimate the whole thing by the same z heavy, but where we substitute t by lambda here. And finally, if we imagine that beta is small and lambda we will take to be of order 1, then we can again dualize this, this partition function and estimate it by the dual vacuum contribution. So we just invert this effective beta. And there's some prefactors which are not too important for these purposes. So this is our estimate. So now collecting everything together, we get this term from the light operators, this term from heavy operators. Also, if you're more careful, you can work out the prefactor beta squared. And so now it becomes obvious that in order for heavy operators to be suppressed, you just take this lambda to be smaller than 2 pi or equal. So 2 pi is the largest lambda that you can take. We will make this choice from now on, lambda equals 2 pi, and we can drop these heavy contributions. And we indeed see that everything is dominated by, well, this is dominated by light, by the vacuum effect.
So sorry, but if you take exactly 2 pi, then it's of exactly the same order?
No, so there's a prefactor which is beta squared, which is smaller than beta 3/2 here.
Ah, okay, thank you.
Yeah. So also you can now take this exponent, and so beta is a free parameter, so you can optimize over this beta, and so that just leads to standard thermodynamic relation between beta and delta. Delta is the center of this interval if you're interested. And so we will also fix beta to this value for now. And you can do a similar thing for the lower bound, and eventually when everything settles, you get just this simple bound at asymptotically large delta. So this number of states in this window is bounded by this rho naught of delta, which is just this thing. Cardi with together with the prefactor. That's actually the naive rho naught that you get from inverting the vacuum. But then you have these prefactors of phi hat plus minus of 0, which is the 0 mode of the phi functions.
Sorry, but there must be an interplay between delta and lambda.
Yes, usually yes, essentially there is a, but
I mean, this formula clearly is not right if you take delta too small.
So, well,
I mean, by
relation,
small delta. I mean.
Yes, there is a relation between lambda and delta, and the relation is that the larger lambda you take, the smaller delta you will be allowed to take, right? And so what we would like is to take the largest lambda possible, and then we can, and this will give us the most freedom in choosing small delta.
No, I'm
Isn't
sorry.
that-
This
isn't that the
formula,
crucial
how can this
point?
formula not be right? It will be right as long as you will be able to satisfy the condition that phi plus and phi minus
Exactly.
are related to the characteristic function of that interval, which you still have not checked. So,
I have not. This will be
so
the
this may or
second
may
part.
not be consistent, but it's as long as you check that condition, this formula will
But
always be right.
that's the crucial condition, right? Because the spectrum is discrete. So if I take delta very small, this formula is clearly wrong.
So the rest of the talk will be
It's not
discussing
wrong.
this
It's
phi
not
hat.
yet made explicit.
I will make it explicit in the rest of the talk. The rest of the talk will be about this, making explicit these phi hats and choosing these phi hats to be specific functions and optimizing. Okay. And this, so the dependence on small delta sits in these phi hat functions, and we will see what kind of phi functions you can take. Okay, does it help?
Yes,
Power?
thank you.
Perhaps just one question. So could it be that in some situations, so you said that lambda 2 pi is what you're going to choose, but it was, what if you chose the larger lambda? Could it be useful in some situations?
So
Small lambda, sorry, I meant small lambda.
No, the best bounds you can get is when you can take the largest lambda possible. So that when you know as much as you can for yes, when you take the largest lambda possible, that you would be allowed to take the small delta smaller.
Yeah,
So
sorry,
this will give you the
I got
largest
it.
freedom in small delta.
Yeah, thank you.
So I'll make this phi hat explicit in the rest of the talk, essentially. So now, indeed, the question is what kind of optimal, what kind of values of phi hat we can get, what kind of functions phi we can choose, right? So this is essentially the question we need to answer in order to answer to have meaningful bounds. And so let me remind you, so what are these functions phi? So functions phi are continuous functions, and we would like them to be integrable so that phi hat of 0 is finite. And so they bound this characteristic function from above and below. And the support of the Fourier transform should be 2 pi, right? That was that lambda that we chose. You can keep it arbitrary if you'd like, but the best thing you can get is from lambda equals 2 pi. And now the question is, so what's the minimal value of phi plus and the maximal value of phi minus hat of 0, right? So to optimize those bounds, this is the problem you would like to solve. So equivalently, what you're doing is you're minimizing this area between the characteristic function and the phi function under the constraint that the Fourier transform has a finite support to pi. So that's the problem you're trying to solve. And in fact, this kind of problem has been considered before, first by Beurling and then later by Selberg. So often called Beurling-Selberg minorant and majorant problem. And so now I will just review. So what is so the solution to this problem is actually known, and I will review the solution on the next slides. Right, but before we move on to the solution, we need one important theorem which will help us. So there's this classic Paley-Wiener theorem. So it goes as follows. So suppose you have a square integral function then its Fourier transform has a finite support lambda if and only if this function phi is extendable to the complex plane as an entire function, such that it's exponentially bounded with an exponent given by the same lambda, which is the support. Okay, so this is a classic Paley-Wiener theorem, and it is extremely useful in practice, in fact, because if function phi is complicated, you actually don't need to compute its Fourier transform. You can just look at its growth at infinity and read off what's the support. So it's actually very practically useful. So for example, let's consider this function, simple function sine z over z squared. So immediately we see that its growth in the complex plane is just e to the 2 pi z. And so therefore lambda is just 2 pi and the support of Fourier is 2 pi. And right, so this is the theorem, and these functions, these entire functions, which are exponentially bounded, are often called functions of exponential type lambda. So we will make use of this theorem in what follows. So I guess I have some time to discuss. So roughly the proof of this theorem, let me just sketch it. One way it goes sort of very easily is that if you have a function phi hat of finite support, then you just take its Fourier transform to compute phi of z, and then it's pretty clear that just because of this exponent that it's bounded by e to the lambda mod z in the complex plane. And the other way is a little more complicated, but roughly the idea is that, so if you have a function phi, which is an entire and exponentially bounded, then you compute the Fourier transform and you can deform the contour parallel to the real line off to infinity. And then because this thing is exponentially bounded, and you also have this exponent, so you can show that it means that outside of the lambda interval, this integral is 0 because you can shift it arbitrarily far. So it's like roughly the sketch of the proof.
Bauer, but why did you say it has to be an L2 function? In any case, you don't need an L2 condition, you just need L1.
I don't need it, yes, but Paley-Wiener general, and because for L2 functions, this relation between Fourier is nice, so this theorem is just more general than that. But yes, I need it only for simpler things. Okay, so now we can actually solve this Beurling-Selberg problem. And so this class of problems is usually from some kind of summation formula. I'll explain on the next slide what I mean by that. So you derive some bounds on that first, and then step 2 is that you just construct these functions phi that saturate the bounds you derived in step 1. So that, and so we start with the step 1, and so for simplicity, let me just interval delta, because this integer use just some summation, so that the sum of
I think there are some
So
issues with your audio.
integers, equals this. Only one term on this left side survives. This is exactly the phi hat. Oh, I'm sorry.
Maybe the bandwidth is too small or something. I think we missed the last minute of what you said. At least I did, and some other people did too.
Yeah. Hi. Do you hear me now?
Yeah, it would be nice if you could repeat like the last minute.
Yeah. Sorry about that. Actually, my internet connection hasn't been good for some reason in the last couple of days. I'm not sure. So where should I repeat?
Like when you started explaining step one.
Step one. Okay. Right. So I was saying that usually these kind of problems are solved in two steps, and step one is you derive bounds on this phi hat from some Poisson summation or some generalization of that. And then on the step two, you construct functions which saturate these bounds, and therefore they're optimal. And so we start with the step one, and here I will consider integer-sized intervals because it's simpler. So we have the Poisson summation formula, and
Bauer, I don't think we see your slides.
Sorry, what?
We don't see your slides?
You don't see my slides.
No, we do.
Did it stop sharing as well?
Yeah.
I'm sorry. Do you see it now?
Yes.
Yes.
Okay. Sorry about that. Okay. Right. So we consider the Poisson summation formula, and we have, because this phi hat has finite support, only the zero mode survives here, and it equals the sum over integer spaced numbers. And so now you also use this phi plus minus bound the characteristic function of the interval. And so from there, you just derive these bounds. That's phi plus is bounded from below by 2 delta plus 1, and phi minus is bounded from above. So let me explain this a little more. So essentially, so if you have an integer-sized interval here, right, and this is a sum, let's say, over integers, then you just count how many integers inside of the interval do you have, right? And that's how you get these numbers. And there's a funny mismatch of 2 because of the edges, because at the edges phi plus is 1 and phi minus is 0. And so because of that, because of 2 edges, there's a mismatch by 2. So you just derive these bounds. So that's essentially the step one. And now the step two is you just construct the functions that saturate these bounds explicitly. Okay, so, and in fact, from the way we derive these bounds from the Poisson summation formula, it's pretty clear what kind of conditions these functions phi should satisfy, right? So I've written them down here, but essentially these conditions are that these functions phi plus minus, they are 0 outside of the interval at integer points, and they are 1 inside of the interval at integer points, and the derivatives are also 0 at these points, except for the edges, right? So these are the conditions you need to satisfy, which I've written here. So now let me just write down the answer, essentially. Okay, so the answer is that is this, and so let me explain this formula. So, for example, for phi plus, and when delta itself is an integer, let's say. So first of all, this prefactor this sign squared, it's 0 at integer points. And so this takes care of all the zeros outside of the interval, which are second order zeros. And then inside of the interval, we need to cancel some of these zeros. And this is the role of these second order poles in the brackets. So they cancel the zeros inside of the interval, and the residue is 1, so that the value of the function is 1 here. And the first order poles here are not allowed because you want also the derivatives to be 0. You can show that, except for the ends of the interval, where you can have first order poles. But the residues should be related so that the function is integrable. And so this essentially fixes this function uniquely, or almost uniquely. Another point is that you can easily check that this function is band limited. So we just read off from this sign, we just see that it grows as e to the 2 pi z in the complex plane. And so therefore, by Paley-Wiener theorem, we know that phi hat has finite support to pi.
What's the value of lambda plus? Is it a fixed parameter or is it an arbitrary parameter?
Yes, let me comment on that exactly. So finally, you actually need to make sure that it bounds this characteristic function everywhere for all x. So we only checked necessary conditions, but we haven't checked that it's this function actually does what we want everywhere for all x. And for this inequality to be true, it's you can check that. It's somewhat technically more involved, but still elementary, and you can show that this lambda should be in a certain range for this to be satisfied, which depends on small delta. And any of this lambda works for this condition. And so for phi minus, there's a similar formula, and there's also a similar formula. For phi minus, the formula is essentially the same, except ends of the interval, you don't have the second order poles. And for half integer delta, you just sum here over half integers instead. So it's very similar. And these functions, by construction, they satisfy this condition that phi hat that the 0 mode is 2 delta plus 1, plus minus 1 by construction. And so therefore, we just take these functions, insert them back into our bounds, and we get these bounds. Okay. Right. So far we've discussed these bounds for 2 delta when 2 delta is an integer, sized. So actually, you can show that these bounds hold for any delta bigger than 0, but they are optimal only for integer 2 delta. So so first, let me comment briefly for how you show that for non-integer delta. So for non-integer delta, so it's not completely trivial to generalize these functions because their dependence on this small delta is not analytic, because it enters in this sum. You sum up to delta over integers. So it's not completely trivial, but you can do a trick. And the trick essentially is that you have non-integer delta, and you write this characteristic function as a sum of 2 sine functions. And then first you construct these functions b, which bound these sine functions. And the way you do that, you take the Selberg functions that we discussed before, and you essentially take one of the edges off to infinity. You just take one of the edges off to infinity, and you get this sign, this step. And then you just sum 2 of such functions, and you get a new function which now bounds an arbitrary sized interval. And you get the same zero mode for that. In any case, the bound is the same. But so now let me make a couple of comments. There are some simple consequences of these bounds, which are nice. So from the lower bounds, it's pretty clear that for if you take an interval which is larger than 1 here, to delta bigger than 1, then in any such interval you will find some states. So it means that the maximum spacing between operators is 1. So that's this thing. For the upper bound, so you can take this small delta to be very, very small, to be almost 0, right? And so that essentially means that the maximum degeneracy of an individual operator is this rho naught. So it's also kind of a simple consequence of this bound. Right. So now we have these bounds, and a natural question is whether there's any interesting partition functions that satisfy these bounds. But maybe before I move on, maybe there are some questions I can stop for that.
Is there any interest in optimizing these bounds for non-integer delta, or is it a purely academic question? Like for not half-integer delta?
Optimization, you mean the Beurling-Selberg optimization for non-integer to delta?
Yeah, that's what I mean.
Yes, we did it. We can also do that. I will discuss it if we have time. Yes, it can be generalized to that case as well, just more complicated, a little more complicated. But so first, let me then discuss. So you can actually saturate these bounds for integer-sized intervals and for central charges, which are multiples of 4. And in this case, so for example, for c equals 12, you can consider this J function, Klein's J invariant, and it has essentially it has integer spectrum, and I will consider it as a non-holomorphic partition function on this slice, which is S invariant, but T invariance is just broken explicitly by this condition. And so it has integer spectrum, and you can show actually that the degeneracies of operators at very large dimensions are given precisely by this rho naught function that we discussed before. Right, so now how do we see optimality then of this partition function? Well, the point is that because the integer, because of integer spectrum, right, and individual degeneracies are these rho naughts, you just count the number of operators inside of this interval, which is precisely this 2 delta plus or minus 1, depending on the upper or lower bounds, times this rho naught, which comes from this degeneracy. So this shows that these bounds are saturated. And in fact, you can do it for any central charge, which is a multiple of 4. You can construct similar partition functions, which are S invariant and have integer spectrum and saturate those bounds.
You write Z, but you really mean positive, right? Integers.
Yes, yes, of course, yeah. 4, 8, 12, so. So somewhat more generally, actually, we can ask, how does saturation happen, right? So if we go back to these original bounds, right? So written here as integrals over delta prime. So the saturation happens actually precisely when the zeros of these functions phi plus minus are at the physical operators, when these nodes, these red and blue dots, are precisely the physical operators. Because in that case, this integral, because you multiply it by the density of states, this integral will not count the states outside, because it's precisely phi is precisely 0 at the operators, and it will count just the operators inside, right? And well, and if you also take delta large beta small, let's say this exponent will cancel this exponent, and so you precisely count these states. And so in right, and so in the previous example, therefore, it was not a coincidence that the Selberg functions were zeros outside of the interval at integer points, and the spectrum of partition functions that saturate those bounds were also integer spaced. So that was two related facts. And this is somewhat reminiscent, I guess, of extremal functionals in the more in conformal bootstrap stories. Right, so that's what happens. Yeah. So now I can also discuss so the non-integer case. So for non-integer sized intervals, so essentially the steps are similar, but instead of Poisson summation formula, you need to use some generalization. Excuse me. So in this case, it turns out that the suitable generalization is this Lippmann summation formula. So let me explain that, which was actually derived somewhat recently. So suppose you have this band-limited function with support to pi, then the following formula is true: that the zero mod of such a function is given as a sum of this function itself at some discrete set of values xn times some prefactor, and this xn are roots of this polynomial. I'm sorry, not of this function, trigonometric function. Right, and gamma and r here, gamma is any positive number and r is any real number. And so you have this formula, and in particular, if you take gamma to be very, very large, you will actually recover the Poisson summation formula, because so in this equation, so only the second term will be important, and so the solution, so xn's will be just integer spaced points, and this prefactor becomes 1, and so you just recover Poisson summation. But this formula is more general.
Sorry, I'm confused. What is R? What is this real parameter? Is it an arbitrary parameter, or is it?
So it's anything. So for any gamma in R, this formula is valid. Just like in Poisson summation, you actually had this parameter R as well, that you could sum over integer spaced points, but there was like an overall shift of all these points. So that's the same R. And gamma is an extra parameter that you can tune, and that essentially tunes this discrete set of xn's that you choose. And so for our purposes, actually, so the rest is kind of very similar to what I discussed before. But so one thing we need to do is that to find actually optimal bounds, what we would like is we want these points plus minus small delta to be among these nodes xn over which we sum. And that will allow us to derive optimal bounds. So if we remember the example of integer sized intervals, there it also happened kind of. So there are two related facts: that the size of the interval was integer, and that the Poisson summation formula was a sum over integers. And these two were related and allowed us to derive optimal bounds. And so here we will demand the same, that this plus minus delta is among the roots xn. So that this b of plus minus delta is 0. And that fixes the parameters gamma and r depending on the fractional part of delta. And so from now on, actually, the rest is very, very similar to the integer-sized interval story. And so I will just let me just write down the answers. So essentially, construct these functions phi plus minus. Just instead of sine squared, you have this function b here, which is 0 on these nodes. And then you also need to add some poles to cancel some of the zeros here. And then these optimal values of the 0 mode are essentially derived from this Littmann summation formula, where you sum it only inside of the interval. And that's essentially the answer. So let me just summarize it on the plot, what we've done. And so we have these bounds.
Hey, Bauer, we can't hear you.
Bauer, I think you disappeared.
Leonardo, can you maybe unmute him or whatever? Kick him out, maybe then he'll realize that he's not heard anymore.
I'm sorry, yeah, my internet is terrible. Let's see, let me try to.
You're back. Yeah, you disappeared for at least a minute.
Yeah.
We haven't heard this last slide which is your money plot. We haven't heard any explanation.
Yeah. So can you see it now?
Yeah, now it's good.
Okay. Right. So we derived this. We have these bounds, and so one simple bound we derived is this red dashed line, and the values of the 0 mode to delta plus minus 1, right? And so this was derived from the Selberg functions, and for to delta integer, this is optimal. And when to delta is not integer, we use this Littmann summation formula to derive optimal bounds in that case. And so this is that is this blue line. And this is all asymptotic at large delta. And this is allowed region. And so this is essentially the summary. And as usual, there are some open questions. So, for example, what is the saturation for? So we show that for some cases there is known partition functions that saturate the bounds, but you can ask what about other values of central charge and to delta, and if they're not saturated by any partition functions, then that probably means that you should take functions phi which are not band limited, but something else, maybe something relax the assumption, and so go beyond band limited functions. And ultimately, this boils down to having better estimates on the form factor, essentially. So if you have better, so we had some very crude, exponentially large estimate on this form factor, but in reality we expect that it's due to the phasing, it's actually small most of the time, except for Poincare recurrences. And then there's also, you can imagine doing some generalization to other correlators or other bootstrap equations. So instead, let me, I guess, just leave you with this summary plot, and thank you for listening.
Thank you. Any other questions?
Yeah, I have a question. So these statements you were making, were they about?
Sorry, can you speak louder? I don't hear you very well.
We don't hear you. We don't hear you.
Oh, okay. Can you hear me?
We do not hear you at all, Nima.
Oh, we don't hear you.
Can you hear me now?
Yes.
Okay. So these statements you were making, were they about Virasoro, or were they? So when you said the spacing was integers, is that because of the descendants, or that was a statement about the Virasoro?
So in this case, I just wanted to consider the most simplest thing. So here I treated both primaries and descendants on the same footing. So I counted them separately. But in principle, you can repeat this analysis for Virasoro, and essentially everything goes through, because it's just slightly more bulky formulas, but yeah, essentially all the results hold in that case as well. Also, you can do it for fixed spin, for example, which we did in our paper.
I see. Another thing, is there so there is a whole bunch of rational CFTs that have integer spacing. Is there any way to use your formalism to not worry about these rational CFTs, and, for example, try to get at maybe chaotic CFTs? Try to say something about the statistics of the high energy states using this type of analysis? I mean, it's kind of a hopeful question, but is there any way to put additional assumptions, for example, on the heavy operators, and then, or to put like to put a gap or something and say something about what the bounds are on the high dimension operators?
Right, that's a very good question. Yes, ultimately you would like to, for example, derive like RMT pair correlators, for example, for high energy states and chaotic theories, but it's not completely clear to me at the moment. I guess the short answer is that I don't know, but naively, yeah, maybe if you impose some constraint that there's no conserved currents, for example, then you can derive something of that sort. But I don't think I have anything concrete to say at this time.
Okay. Thanks.
Yeah, I actually had a similar question. I would have thought that this averaging window to little delta, and then non-integrable theory could perhaps be made like exponentially small as you take big delta large. Is this something, yeah, like perhaps imposing the absence of conserved currents or a twist gap is sufficient, but is this something that you guys have explored at all? I guess you'd have to know about the spins at the very least.
No, I don't think I have anything to say at this point. Yeah.
Yeah, you did not mention the generalization to spinning partition functions or two variables partition function. Is that very hard?
I haven't mentioned, but we actually did it in our paper. No, it's similar. Yeah, it's similar. Yes, there's some slight differences.
Yeah, somehow you might hope that putting in a twist gap might be essential in this story.
Right.
But yeah, I agree that from what you've said, it's not really obvious.
So, well, what I guess I can tell you. So maybe something somewhat different, but maybe related. So this kind of inequalities. So let me go back to this thing. Yeah. So this kind of inequalities. There's a literature on in Riemann zeta function, right? So if you consider zeros of Riemann zeta function, so there we also it's a famous conjecture that there's a random matrix statistics there, right? There actually to derive, so it's not been derived, these pair correlations, but there were some bounds derived on pair correlations. And so if you think of zeros of gamma function as analogous to the energy levels, right? So what's actually been derived is that you have some similar kind of inequalities. But in the middle here, instead, you have a pair correlation, right? So you have two rows, and then here, instead, you have the Fourier transform of pair correlator, which is the spectral form factor, which is the absolute value squared, or just this thing squared, right? And so people in this zeta function literature, people use this kind of bounds to derive inequalities on pair correlations there. And also use this kind of Selberg or Selberg functions, right? The same function that we use. But eventually in those stories, everything boils down to estimating this form factor. And the better you can do it at longer times, the better bounds are. So if you somehow found some conditions that roughly say that your theory is chaotic, so that this form factor has the correct features, namely this ramp and plateau features. So if you somehow derive that, then then you can show that the pair correlations are there. And usually the way people do that in zeta function literature or in chaos literature is that they have usually they use these trace formulas, this Gutzwiller trace formula or Selberg trace formula, this kind of, and I do not know whether this can be done in the conformal field theory, but I guess it would be interesting to see if there is anything similar here.
Yeah, absolutely. Thanks for the answer.
Any further questions?
I have a question about Littmann summation formula. I'm quite puzzled. So okay, we have Poisson formula, which is for uniform sequences, and then now we have this Littmann formula, which is for some very special non-uniform sequence, which solves this transcendental equation.
Yeah.
Can you say like what is so special about that particular transcendental equation, and why was it that equation that? Is there a family of formulas for other equations as well? And like, what's so special about this one? Why this one was useful for you to solve the non-integer delta case?
I don't think I would have a very good answer to your question, I guess, but practically it was useful that so you have some kind of formula which is a sum over some discrete set of points, and this size of the interval, this plus minus small delta, was among these nodes over which we sum. So practically this was what was useful. So I suspect you
why
might
did
not
you
be
use this
satisfied.
formula and not some other not some other summation formula? Or is there just this one? Is this the only one apart from Poisson, or are there some other formulas like this?
I do not know any. So this is the formula. So this is not. So this is generalization of Poisson formula for functions of exponential type, for these band-limited functions, right? So yeah, my answer probably doesn't satisfy you, but maybe I can make another comment about this formula. At least the way sort of people think about this, mathematicians sometimes think about this formula, right? So where I can tell you maybe a little bit where it comes from. So it comes roughly the interpretation of this formula is that there's some underlying Hilbert space, that there's some Hilbert space of functions of exponential type, and then let's say this phi hat was like a norm squared of some function. Okay, imagine this phi hat is a norm squared of some function. Then this right-hand side has an interpretation as a decomposition into an orthonormal basis on this Hilbert space. So it's and these are yeah. So there's the branch Hilbert space of entire functions, which sort of where this formula ultimately comes from.
You have no proof that this gives the optimal bound, right? So this could just be. Do you? I mean, you haven't shown saturation.
No, well, for the bounds with band-limited functions, it is optimal. It's just the same as that. First, you derive the from this formula using.
No, but there's no statement that there is actual physical physical.
Yeah, that's true. That's true. It's just it might be that. So among the band-limited functions, for band-limited functions, you derive an optimal bound. You just don't know if a band-limited function is enough to derive a bound that is saturated by an actual physical partition function. That's true.
But you know what this sequence xn is. Could you imagine a CFT which has the spectrum where these xn's are? No, because if it's any CFT will contain at least some states which are integer spaced, while xn's are not integer spaced at all. So it looks like whatever saturates the bound cannot be the CFT spectrum.
Right. I doubt that I doubt that there's a physical partition function that saturates these bounds. It's just this formula and these bounds solve a mathematical problem.
But you could circumvent this objection by studying the problem with Virasoro primaries.
You can, yeah. Also here we actually require only scaling symmetry. We don't require full Virasoro. So you can imagine there's a partition function which doesn't have Virasoro symmetry, but which is S invariant, which is modular invariant, and it has this kind of spectrum.
Anything else?
Sorry, I have a question. Do you know if one can use the techniques that you use here, so Beurling-Selberg extremization, to derive Hellerman type of bounds? So instead of going at infinite temperatures, go to some self-dual temperature. So in other words, don't work at large delta, I guess.
Right. So I guess in principle you can imagine taking. You can imagine, I guess, taking this kind of formula, right? Or for this kind of formula, which is true for any delta.
Right.
It's just an exact formula. I guess you can imagine then, for example, taking this interval to be just from up to some first primary or something like that, right? And then trying to derive some bounds from this kind of reasoning, but I have not tried that.
Maybe I can choose the phi hat to be just delta function support at the self-dual temperature, I guess, or something like that. I don't know, just saying. because you want beta to be 2 pi or the tau, the modular parameter, to be at the self-dual point, tau equals I. But anyway, I don't know, I'm just saying.
Yeah, well,
Okay, thank you.
Okay, so if there are no further questions, we can thank Baur very much. Very nice seminar. And we will not have a seminar next week, but stay tuned for a seminar 2 weeks from now. Thanks, everybody.
all right, thank you.
Bye.
Bye.